Erwin, thanks for meeting. Right, as a facade designer, I did now engineer it from my side, but you're a structural designer. So as a structural designer, you have to evaluate what I did. You need to address where I did wrong and where I need to take care. And with that, I'm going to then redesign. The system we made a selection of aluminium system, a wood system, a steel system, and we decided for the aluminium system. And this is the request. It's a rather simple problem. We have concrete walls, so it's good to fix. We have an opening of 620 by 420, so this is not too complex. This is the grid which was decided. We made it 220 because we want a door in here. And then, a meter something for the horizontal grid. And then we made a decision about the system, aluminium, as said. And we need to think about the tolerances. So this is where concrete is supposed to be, somewhere in this range. And then the facade system is with a certain distance. We decided 2.5 centimeter, that's the distance from the main grid as the system. Is this kind of, tolerance decision okay? Would you expect more tolerance in concrete?
No, the tolerance is okay. I think we should have a look at how we connect or keep this million free from the concrete.
Yeah, so expecting this is the distance, so even if concrete goes very much inwards, it still has a distance.
Yes.
So in that respect, this is kind of okay from your side, which is good. Happy to hear. Makes less details to change from me. This is the overall final layout. So we ended up with this grid system, with this horizontal line to 20 for the door. We're going to see the door later.
Yeah.
And now the detail.
These are operable doors, not sliding doors.
Not sliding doors.
Okay.
What would you do with a sliding door?
Well, that's depending on how you would organize the whole system. I mean, you could, if you have sliding doors, maybe you could have a more heavy transom and less mullions to make it sliding happen.
Which means a heavier transom, taking the dead loads from the top.
Yes, correct.
And then allowing not having mullions here and here at these places.
Correct.
So that this door could horizontal slide.
Yeah, and maybe you could even hang the transom to the roof. But you have operable doors, so you don't need it here. But it's always to keep in mind.
I fancy this engineer because you're giving me opportunities to redesign. Very nicely done. We keep it simple. We keep normal openable doors with a normal stick system, mullions and transoms as they are designed. So in, say, the setting, yes, the inner one is having less, which means that the horizontal loads of this one are going to this one as well. So we need to take at least care of that load situation once.
I think you made a detail of that one, I hope.
Yeah, you're going to see later.
Okay.
Okay, right. So then we made a decision about the details. We decided to do, say, the standard detail, bottom, top, side, and the door with some details. Of course, you can do a lot more of these details. Are you okay with that?
I'm okay with this one, yes.
Yeah?
Yes.
Okay.
Yes. Yes, as structural engineers, you always think about the mullions and transoms. So in a way, you would like to see how these two connect. Maybe we can sketch something later there.
Yeah, let's see. Here we go. This is the connection. And what we did is we took it from the catalog, a typical work which you do in this situation. You start with, say, a standard detail, the aluminium stick system, horizontal cut, and then the connection comes out of their system.
Yeah.
So if I go for the aluminium system, they have a certain connection point, which then takes a certain quality of loads. If I come from the timber, again. If I come from the stainless steel, again as well. And then I have to believe that somehow this load transfer can deal with the loads I'm giving to this. Do you agree? And do I have to take care of something?
Mullions are there for two reasons. The one is taking the vertical load of the whole system, and the other one is the horizontal load, which comes from wind.
Yes.
So it has to be strong enough and stiff enough to hold those forces.
So dimension of this needs to come from the catalog, I guess.
Yes, because it can deform. By wind, it might deform in this way.
Yeah.
And if it goes too far, you feel uncomfortable, unsafe.
Yeah.
So it should be stiff. And the other one is you have vertical load. So there's a vertical load coming down.
Which means this way.
Yes.
and this way.
Correct. And what it has to do is, okay, first of all, the vertical load only comes from the weight of the glass and the system itself.
So how does the load of the glass find its way in transom and malleum?
That's a good question. Maybe we can go back to one of the previous. Yes, I think I like this one.
Okay, go on.
If you would have, let's say, this panel here, it's a glass panel, and what we usually do is to have two plastic blocks, approximately 10 centimeters from the vertical edges. There it rests on the transoms.
I see. Okay.
And then the transoms transverse it to the mullions again.
I see.
So the load path, the first one is, it's going to rest
Yeah.
on the transom, and from there on, it goes further and it will rest on the mullions. That is how a vertical load of a glass panel goes down to the foundation.
Great. Which means in this detail, we somehow have to have something here.
Yes, you should make. You have to get to here some plastic blocks there.
Which actually on top of this, we're going to see them in the vertical section. In a minute.
And of course make a good connection where this transom connects to this vertical mullion.
See. So
those are two very important structural.
Go down here, then they're transported sideways, and then they go down.
Correct.
Here.
That's the vertical one, and additionally, you also have to see if it doesn't if you have this horizontal load, if it doesn't deform too much. Yeah. And I think we'll get there when we have the detail of the tolerances where we hit the concrete wall.
I see. And again, I'm going to take this as a given system, so I'm going to check the system provider's information to see how wide I can go with what kind of dimension and how deep I need to go for what kind of dimension of this. Okay.
Yes, and I think we see here the aluminum system, and of course you also have wood and steel, and it has to do with elasticity.
Of course.
So that's why
the different materials have different elasticities, which means it gives different dimensions.
Yes.
Bluntly speaking, the aluminium one is a lot wider because it's weaker as material versus the steel system.
It's a factor of 3 in stiffness.
Or the other way, I can go higher with a steel system with the same dimension.
Yes.
As I say, principal rule of thumb. Okay.
Yes. So if you would simplify, so you would expect that this one has the least dimension. This one will be slightly larger, and a wooden one would you
expect to be larger?
That's my first expectation.
Okay, for the same height.
For the same height.
For the same height for the structure. Okay, that's a good one. So going back to this one. So this is the main detail. This is now a connection to the top.
Yes.
And here we again talk about the tolerances. We had this integrated, so we said this is 1 centimeter, 1 centimeter, where the concrete could find its position. In the final situation, we still deal with the same aluminium piece. And we need to get this airtight, tied to the outside as, say, a normal facade system. Any aspects from structural design which we have to take care of?
Yes, well, I will ask you a question. How many vertical weight is here at this top from this facade system?
From the system, there's no weight.
Yes. So what do we have to solve then?
That's my question. Do I have to solve something in this direction? No. Do I have to solve something in this direction?
Yes, correct. Yes. Here you only have horizontal wind load. And of course, the system itself weighs a bit, but that's not a big issue. So here you have to solve the horizontal force, and you have to connect that
to this counterpart, which is the concrete.
Yes.
Okay, these two have to be connected.
Yes.
Again, the catalog will supply me systems, so there's some kind of connection detail which is to be integrated here.
And if I would finish this detail, you could also draw the mullions here. So there are always mullions. So you could also maybe connect the mullions a bit further here. So it's a good idea to connect.
So it may end up in, say, the mullion going on this way, and then there's a shoe with a sliding piece inside,
for instance,
allowing that this movement of the main structure doesn't hit the system itself, but allowing that horizontal forces are taken.
It's like a dowel.
And then there's maybe some kind of connection in here.
Yes. Let's call it a
dowel.
A dowel.
Yeah. Great. Top. Bottom.
Yes.
When I rephrase your question about the loads, yeah, I have the horizontal loads.
Correct.
And I have the vertical loads.
Yes.
So somehow say these loads need to be taken and these loads need to be taken.
Yes.
What is your answer?
My answer is you could do. I always think in options. Do not always give one solution, but try to have more options. One of the options could be if I have again the mullion where all the forces are in. Okay. You might have a support in this area. Mm-hmm. For instance, a block of insulation which is strong enough to hold the forces.
So a solid block of foam taking the whole structure.
Yeah, why not?
Huh, okay. No point load problem, it just will, okay. Which actually would also fill this part, which then would increase my U value.
Yeah, and you have no bugs.
Mm-hmm. And I have no bugs. True.
Yes. The other way could be to only support the vertical mullion. Mm-hmm. Yeah, for instance, all the loads come down and I might even support it here. So all the forces go down here. And I have a kind of pedestal, a kind of footing, mm-hmm. where it could rest.
Can I do the same as I did at the top, where I have the mullion being longer and then some kind of dowel-like situation which I fix?
That is also a good idea.
Mm-hmm. And then I fix it here, and then I have, say, a structure which is fixed to the side. I can actually move it before I fix it. And then I extend the facade system and fix it with a final screw in position. Yeah. And then the difference is that this is fixed, so forces down, while this is still allowing that the main structure moves and doesn't give the force to the system.
And one way of moving that we didn't address yet is rotation. I mean, mm-hmm. Since from the horizontal wind load it will try to bend.
True.
It will this will give a certain rotation.
Well, hopefully not that much, but kind of.
I'm just exaggerating just to make it clear. Yeah. So at this position, you need a kind of soft material that knows how to.
Which I did.
That's fair. You did. So it's very important to keep certain distance there.
There's potential for
that's for rotation of the mullion.
Did you do the same at the top?
Of course you did. I already checked that. I already checked that. I saw that.
Thank you. Okay.
Well done.
Okay, this is done. Now side. Rephrasing your question, what kind of forces? We do have forces here. We don't have forces in this direction. Yeah. So only this kind of forces. Yeah. As it is now taken at the top and the bottom, do I need to fix it here?
Yes, I would like to. And it not from a structural engineering point of view, but more for weather tightness.
I see.
If this one starts to move a lot, you can imagine that it's very hard to keep this detail watertight.
Okay.
And you would also like to keep the dimension the same for each mullion. So to keep that the same, you would have a connection to the concrete here. That's very important.
So I'm somehow going to do a connection like this, and I still need to work with tolerances.
Yes.
So I allow this to be fixed finally in the end.
Yeah, and so you have here, it's slotted like here, mm-hmm. so it can move a little, but this one is really fixed here and will be fixed there.
Okay.
And that way, so it's to do that the horizontal forces that come here can be taken to there.
Check. The door.
Yes.
Well, this pretty much comes from the system.
Yeah.
So system supplier provided a certain detail how the door is brought in. Anything I have to take care of here, I say sketched where the hinge would, for example, be. This is quite heavy. So when I think about the whole geometry, this door is what, 200 kilo, 300 kilo?
Yeah.
And me even hanging on makes it another 100 extra.
Yeah.
So the hinges need to take a lot of force. When I think about the hinges, I imagine this goes horizontal.
Yeah, but then in the other direction. I mean, we had the wind load, which was in this direction. Yeah. But if you had the hinges, it's, I think you all know it, I think from our own kitchen, the doors always start to hang. So there will be a horizontal load here. So it needs very good connection there.
And when we draw it in here, what does it mean?
Yeah, it means that if I would sketch the hinges, I think I would expect hinges there and there. Yeah. And what it tends to do is that the whole weight of the door is in the middle. Yeah. So what it tends to do is give a horizontal force in that way and one in that way.
Yeah.
So you have to fix it very good to the mullion.
See.
And what it needs is this horizontal force. I have to get that one back
This direction.
in this direction. So this one is connecting the mullion to the transom is very important at the door section.
And that means that this detail at this situation also gets forces.
Yes.
Aha, this is interesting. So in this respect, it's not only about this direction, it also starts to become an aspect for this kind of direction.
Yes. Be aware.
Side note, for the experts, we're not taking anything into the glass. So the glass doesn't take any of the loads in this system.
I would love to, but
you would love to. That's just,
that's why we're here, because everything is in the glass.
No, not here. Not this in this course. Maybe somewhere else, but not in this course. Okay, so we talked about this detail, the door detail. Again, I rely on the system supplier. So I take the material the system supplier delivers, and then I'm done. And then there's the final one, the bottom one, which I think is not that much important for you, because we have, say, a typical detail of the system supplier for the door, which mainly is about water tightness and air tightness as a setting.
Yes.
Yeah.
And of course, I always would like to see them as a structural engineer, because then I know that I'm complete.
Thank you. Let's take a look at the brief. Dead load we talked, payload we talked, impact we talked, horizontal, vertical load transport, movement of the building, movement of the facade.
Did we talk about movement of the building?
Didn't we?
No.
Okay, well, we took care in the details.
Yes.
So looking at this,
Yeah.
if the building moves, it's not allowed to deliver any forces to the facade.
Yeah.
So when I think about the detail we drew at the top part, which is this one,
Yes.
it allows that the building moves while the facade stays solid.
Yes.
So no impact to the facade.
No.
Which is one of the most important aspects of facade engineering. Facade is standing on itself
Yes.
and not taking the loads of the building.
That would be the ideal. And I think you did a great job here, because you have insulation here. So if a building can move by a difference in temperature, and since insulation is on the outside,
True.
the temperature difference in temperature will be very small. So the building will not move a lot.
Get it. Okay. Erwin, we're done. Thanks.
Well done.
This was perfect.
Yeah.
Thank you. You're a good engineer.